Learn we're now, oh, have you started yet? Okay, we are starting chapter 8 now. Chapter 8 is the last thing we're learning for this year, and it's involving two things. Number one, improper integrals, and number two, some other techniques of integration that we haven't learned yet. Techniques like partial fraction decomposition. Or did we do no, we didn't do partial fraction decomposition, did we? I don't remember. But anyway, but I think we're doing partial fraction decomposition, and then we're going to learn how to take integrals of really, really hard trig functions. So actually, frankly, it's a very fast sort of chapter. You know, I don't even cover all the sections in chapter 8. Just a few sections that are on the AP exam. So, you know, the bulk of what you need to know for the AP exam, of course, we've already learned, particularly chapters 9 and 10. But anyway, let's start with improper integrals, okay? An improper integral is one that has infinity as one of its bounds, or one where there's a discontinuity within the bounds. Like you're taking the integral from 0 to 10, but your function is undefined at x equals 5. That sort of thing. So I'm going to teach you how to do these, but I'll tell you what, I'm going to teach you the easy way. For example, if you've got an integral with infinity as one of the bounds, you know what you do? Plug in infinity. You know, I don't do any trickery, any mathematical trickery, just stick in infinity. So hey, let's get started. There's an episode of Kim Possible. Did I ever tell you about that? No, okay. There's an episode of Kim Possible. It's the one, I don't know if you remember, but there's this talent show, and she has to get to the talent show, but Ron Stoppable ends up like extending his act for hour after hour until finally Kim Possible can get there and sing her awesome song. How many people remember that episode? Okay, one of you. It used to be, people remembered it better 20 years ago. But yeah, so I love that episode, and Kim Possible ends up like singing this incredible song and totally wowing the audience, but first prize went to Ron Stoppable because the judges say, proving again that quantity is more important than quality. You know? But what kept Kim Possible back was Dr. Draken. I don't know if you remember Dr. Draken and Shigo, you know, his kind of a partner. They had her trapped, and he says, here's what I'm going to do. I'm going to make a bottomless pit, then I'll fill it with water, and then I'll ice the surface of the water, and then I'll throw Kim Possible in with a mutant squid, and then ice over the top of the water, and she'll never be able to get out. And Shigo asked Dr. Draken, if it's a bottomless pit, how are you going to fill it with water? And Dr. Draken, you know, gets disturbed by that and just passes it off. But that's actually a calculus question. Is it possible to have a bottomless pit and yet have a finite volume so you can fill a bottomless pit with water? Is that possible? Okay, or another way to put it would be even simpler. Let's go 2 dimensions. Is it possible to have an area with an infinite perimeter? That is it possible for me to have an area that is surrounded by an infinite amount of fence, but only has a finite area? You know, is that possible? Well, the answer is yes, it is. It is possible to have an area of prairie, let's say, with an infinite amount of fencing, so your prairie whatever goes on forever, but it only has a finite number of area. And let me show you why. Yes?
Would it just be like a really skinny rectangle?
Absolutely. Omar says, would it be a real skinny rectangle? And yeah, it's that sort of thing. And here, let's go ahead and do it. And believe it or not, you guys can do this example without any prompting from me. Here it comes. The integral from 1 to infinity of 1 over x squared dx. Okay? That is, I've got myself here's 1, 1. Okay? I've got myself a prairie. Okay, or I don't know, animal pen, a region that has an infinite perimeter. So this is a region whose perimeter goes on forever. So I'd need an infinite amount of fence to surround it, but is that area finite? Please do this problem now. And you're just going to plug in infinity. Hey, are you guys getting +1?
Yes.
Hopefully so. Yeah, because you stick in infinity, and 1 over infinity is 0. So it turns out, yes, this would have a finite area. It would be 1. So the answer to Shigo's question, can you fill a bottomless pit with a finite amount of water? The answer is sure. Just make sure your bottomless pit follows that sort of formula. You know, like if I were to rotate this about the x-axis, I haven't actually done the math, but I wouldn't be surprised that I would now have a volume. If this were Dr. Draken's bottomless pit, it would still be filled with a finite amount of water if I added up all the disks. I haven't actually done it, but I suspect it would. Okay, so hey, let's do more problems involving infinity. Here, try this one. The integral from 0 to infinity of e to the negative x dx. Go ahead and do that one. And again, the answer is just stick infinity in. Don't do any limit. I'm going to show you some limit stuff, but right now, just stick in infinity. Why not? Who's going to stop you? It's not against the law. Are you guys getting 1? Because e to the negative infinity is 0, correct? I mean, that's e to the negative infinity is 1 over e to the positive infinity. And 1 over e to the infinity power is 0, you know? 1 over a million, billion, trillion, quadrillion is 0. Great. Hey, we can even do this where I have infinity as both bounds. What if I have the integral from negative infinity to positive infinity of x over x squared plus 1? Okay. Well, which technique of dx, which technique of integration am I going to have to use to do this problem? Yeah, substitution. I'm going to let u be x squared plus 1. I'm going to let du be 2x dx. And so I'm going to have to sprout a 2. There's my 2, which means I sprout a 1/2 out there. Also, at this point, I could do a change of bounds, right? If I did change of bounds, then when x equals negative infinity, what would u equal? Yeah, infinity squared plus 1, or positive infinity. And if x equals infinity, what would u equal? Infinity. So I've got an integral from infinity to infinity. Well, I don't care how big the number is. If I'm taking an integral from one number to the same number, what's the answer going to be? 0, right? But let's say we didn't do change of bounds. I just want you to see, if I do change of bounds, I see immediately that the answer is 0. And the reason the answer is 0 is if you were to look at the graph looks like this sort of thing. So, you know, you just get this incredible symmetry happening, you know? What's that? Yeah, this ends up being 1/2 the integral from x equals negative infinity to x equals infinity of du over u, which ends up being 1/2 times the log natural of u from negative infinity to infinity, and that's equal to x. And so now I can back substitute x squared plus 1 for u. So I got 1/2 log natural of x squared plus 1, and I don't need the absolute value symbols because x squared plus 1 is always, always positive. And so I got 1/2 log natural of, infinity squared plus 1 minus 1/2 times the log natural of negative infinity squared plus 1. And any way you slice it, and any particular number you happen to choose for what your infinity is, this is exactly the same as that. I don't care how big those numbers are, this big number will be precisely the same as that, and you get 0. Yeah. But you could have got that just by doing change of bounds. Okay. So that's the big, the big lesson I want you to learn on this is that 90% or 95% of the time when you're presented with an improper integral involving infinity, just stick infinity in and you'll be fine, Now, sometimes you end up having to do L'Hopital's rule because you end up getting infinity over infinity as your answer. Let me show you one of those types of crazy problems, okay? And I'm just going to do it. I'm not going to have you guys do it. I don't know which example this is, example number 4. Let's say I have the integral from 1 to infinity of 1 minus x e to the negative x dx. And it turns out I do integration by parts. And just believe me when I say that this ends up being x e to the negative x evaluated from 1 to infinity. Just believe me. I do integration by parts, where it turns out this is your dv and this is your u, and you end up with that, okay? Here's the problem. If I can rewrite this x over e to the x evaluated from 1 to infinity, then I stick in infinity, and I'm going to have infinity over e to the infinity minus 1 over e to the 1. And this is infinity over infinity. This is in indeterminate form, okay? But I'm hoping your experience with L'Hopital's rule can give you insight. Actually, even though this is infinity over infinity, can you tell me just immediately which infinity is bigger, x or e to the x?
E to the x.
Yeah, e to the x. E to the x is infinitely bigger, right? So you know this guy's going to go to 0. So you're going to have to use your knowledge of the hierarchy of infinities. I just want to remind you, the limit as x approaches infinity, the log natural of x is way infinitely smaller than x to the n power, which is infinitely smaller than n to the x, which is infinitely smaller than x factorial, if x happens to be a integer, which doesn't happen very often. It happens with our sequences of series. But just remember that hierarchy and you should be fine. If I happen to have the limit as x approaches infinity of x squared over 2 to the x, I know that this is going to be 0, because I know 2 to the x is infinitely bigger than x squared. So just be aware of that, when you get presented with these L'Hopital rule situations. Okay. Let me see. You know what? Let me give you another example. How about the integral from 0 to 1 of dx over rad x? What's the problem with this integral? Where's my difficulty going to come from? What's that? Yeah, I'm dividing by 0. I've got a vertical asymptote at 0. I'm asking you to find the area, under this curve, even though the left bound goes up forever and ever and never reaches the x-axis, right? Well, you know what ends up happening? Just mindlessly take the antiderivative, stick in 0, and everything will be fine. So, I don't know, I really think you could have almost done this homework without me really having to give you much guidance. Just do what you would do had you not learned anything from me, and I think you'll be fine. So, bye-bye.